So in this module, we'll be discussing with bivariate models and multivariate models. Now, before we start discussing the models, I'd like to explain why we use models and why we use predictors as opposed to just looking at variables without predictors. Well, the best way to explain this is with an example, and the example I'm going to use is the dependent variable we'll be using for the rest of the module. So this dependent variable has quite a bit of variability to it. It starts around negative 633 and the values range up to 58k. So if I wasn't using a predictor, the best guess I'd have for any of these individual numbers would be our measure of central tendency. In this case, our mean. So the mean is around 26k, and if you try to use 26k to guess any of these predictors, most of them are going to be way off. So here, for instance, you're going to be off by around 25k. And there's a bunch of errors that occur in multiple positions here. So how could we be a little more precise about this? Well, one method we can use is to use predictors, and that's what we're going to do with regression. So with regression, we can use either one predictor or multiple predictors to predict an outcome variable. Now, if you use one predictor, that'd be a bivariate model. If you use multiple predictors, that'd be a multivariate model. Now, you can't just throw around dependent variables and dependent variables into these models without looking at them carefully, because we can start to do is violate assumptions of a linear model, and that can lead to errors of inference. When you're looking at these models, it can also affect the power of the data. So the main assumption that's violated all the time is that all variables are measured without error. Now we really don't get this at all in social science. And even in harder sciences, there's still going to be error measured in the information you have. However, the more error you have in measuring your variables, the less confident you can be in your inferences. Also, your dependent variables should be quantitative, continuous, and unbounded. Two of the ones I want to pick up on are continuous. So a lot of times we use stuff like Likert scales. Technically, Likert scales are interval data, and those are technically violations of regression models. Also, data should be unbounded, so having stuff like ceiling effects and floor effects really do affect the quality of your data. Your independent variables should be either quantitative or dichotomous. So they can be dichotomous, and I want to pick up on this because a lot of times people think about ANOVAs as factor-based, and they don't use them with regression. However, you can use ANOVA-style analysis in regression. Anything that can be done in ANOVA can be done in regression. Now that we've covered the big ones about linear models, I'd like to go over some of the smaller aspects, which really do affect our data, and some of these which will be covered, violations which will be covered in this upcoming analysis. First of all, data should not be multiclinear. Your independent variables should not be multiclinear. What this means is that your independent variables should not correlate with each other. Also, there should be no serial correlation. So your errors, or the residuals that you have, should not correlate with each other. If they start to correlate with each other, we have serial correlation, and this is usually due to model misspecification. Your errors and the residuals should be homoscedastic. What that means is there should be constant variance among the errors, where there shouldn't be a little error at one place and a lot more error in another place. What happened there is we actually would have varying confidence on our line of best fit, depending on where in the line of best fit we are at. It's a little hard to explain this without a graph, and I'll bring that up in the actual assumptions. However, what we shouldn't think about on this is that this happens a lot with time-oriented data. So if you're doing a longitudinal analysis, you really have to pay attention for heteroscedasticity. Also, your errors should be normally distributed, and we'll go over those when we're looking at our linear models. So first of all, before we look at linear models, I like to plot the data. So let me go ahead and plot our data. And bring up the plot so we can actually see it. There we go. So there's one thing that really strikes me off the bat is that x1 and x2 are pretty much perfectly correlated with each other. And those are both independent predictors. So what we have here is multicollinearity. And I'll get into that when we look at our multivariate model. But what I can say right now is if we run both of these in the multivariate model, we're going to have a big problem. So that's one thing that we really have to keep note of. Also, we're not seeing very strong correlations with any of these to the y variable. Over here, nothing looks really strong. And so I really can't tell right now if the models are linear or not because it's such a weak data set. Now on to our linear models. So this is the first linear model I'm running. We're looking at x1 predicting y. So this is going to be a bivariate linear model with one predictor. Now, one thing, I'm going to go ahead and go through a summary of the linear model, and then I'm going to go into diagnostics. So first of all, here's our estimate. Our estimate is showing a significant intercept where we'd expect when x equals 0, x1 equals 0, our value of y should be approximately 21,000. And we're seeing a standard error of 3,600, and this is showing basically our uncertainty about how close we are to that 21,000. And we have a p-value of that's significant at the 0.001 level. And what this is showing us is that there's a very small chance that this data would be observed if the null hypothesis were true. And again, on this one, we have 0.02 value. So it's showing there's approximately a 97% chance that this data would have been observed given the null hypothesis for the x1. Now with the x1, for every one increment of x1, we'd expect a 111 increment for y. And we're seeing a standard error, again, same with the intercept. And that's the basis on reading these linear model tables. Now, a couple things that would need to be mentioned are the multiple r squared. So multiple r squared is showing 0.2429, multiple r squared and adjusted r squared of 0.2009. The adjusted r squared is a penalty. This penalty is normally due to the amount of independent predictors that are present in the model. It can also be heavily affected by multicollinearity, which we'll get into later. So if we look at the multiple r squared, again, with the adjusted r squared, this model's predicting approximately 20% of our data. Now let's go ahead and run diagnostics on this. So if we look over here, this is showing our predicted values versus our observed values. And what we'd like to see is these dots being pretty much scattered evenly along this entire line. If they're not, what we're finding is non-normality of residuals. And we are seeing that, where a lot of the residuals are being placed along this side. Also, the residuals over here are mostly being carried out by 4 observations that are also high. So this is showing a non-normal distribution of residuals. And it's going to be much clearer when we actually look at the plot. So I'm going to go ahead and plot our linear model with the caps locks. There we go. So if we look at this plot, we see that the residuals are being pulled upwards at the ends, and they're being pulled downward at the middle. So this is definitely showing non-normal distribution of residuals. We're also seeing in the QQ plot that we have a bit of an S-curve, and this is showing us that we have a bit of kurtosis in our model, possibly. And in the previous plot and in this plot, we're seeing 1, 2, 3. The 4, 11, and 16 observations are outliers, and they're affecting our model in a bad way. So we're also seeing here scale location, we want a straight line, and we're not getting that straight line, and we still have these 3 observations, which are skewing our data set. And the residual versus leverage is really bringing that point home, where this is Cook's distance, and these 2 dots are getting very close to Cook's distance. So what that's saying is that these points have both significant leverage and significant deviation from our normal residuals to be problems in our data set. So that's about a pretty big summary on what our linear model is looking like. So one thing the optional reading mentioned that we can do to help improve our explanation of this data is you can use nonlinear transformations on these predictor variables if you have these problems of non-normality, or nonlinearity. So for instance, if you had a curvilinear relationship, it'd also be a good idea to run these models. It was really hard to detect if we had curvilinear relationship or linear relationship in this model in particular because the scatter plot itself was pretty weak in general. So, but what I did run a nonlinear regression, and I did find some pretty good results. So let's go ahead and take a look at that. So if we see right here, we're seeing adjusted R squared go from 0.2429, or multiple R squared go from 0.2429 to 0.3842, and adjusted from 0.2009 to 0.35. So it's a pretty big improvement. And this was done by squaring our x1 value. So that's what we had for the basic values. Also, I want to point out, now that we're talking about adjusted R squared, is even though this is predicting a relatively small amount, one thing our optional readings mentioned is that it was about baseball, so I didn't quite gather the details of baseball since I'm terrible with that, but even if there's a small amount of variance explained, those variances can compound on each other, causing pretty practically large effects, even if it's a small amount. So let's say this was a learning paradigm, and people were learning a little bit more every single time. That could accrue over time and cause a pretty large effect. And they're seeing the same effect with skill and baseball players, where they're just doing a little bit better every single time than normal, but that was producing very large effects in the long run. Yep. Now on to our multiple regression model. So let's go ahead and clear this up. So I ran our multiple regression model, and if we're looking again, our adjusted R squared is taking a big hit. So before we had, well, let me just bring up the summary of our first linear model. Our multiple R squared is explained a little bit more here, but that's just because we have redundant variables. But our adjusted R squared, because of these additional variables, is taking a gigantic hit where this is only predicting 14% of the variance in our model. The reason is x1 and x2 are highly multiclinear, and we can see this as a big effect by looking at the variance inflation factor of our linear model. So if we look here, we'd want around 1 for our variance inflation, and x3 is showing us that. But x2 and x1, 348, 353, this is absolutely unacceptable. One of these variables needs to be destroyed because they're the same thing if you look at them. So that's the big problem over here. Now let's go ahead and run our diagnostics again on our second linear model. And here we go. We're seeing pretty much the same effects. So we're seeing that S shape. We're seeing the not normal residuals. And we're seeing similar effects with our residuals and leverage. So that's not really that different. There's a reason for that. Because x1, x2 are the same variable, and x3 is noise. The reason I say this is if we look at the linear model of y to x3, given the data set equals that one, and a summary of it. We can see that this really isn't predicting anything at all. Nothing at all. So that's the basics of our multiple regression model, where what we're seeing are the implications for this is that our bivariate model is a much better candidate than our multivariate model, given that we have one part noise and another part of the same variable, where we have two useless variables in our model and it's causing havoc among our model and among the way we can explain it. So also, I'm speaking of explaining, one thing that has to be noted is when you're doing these sorts of analyses, it's really important to understand the ecological validity of our data. And that was mentioned in one of our optional readings, where linear models, they're saying that linear models don't necessarily imply causation. Because what really implies causation is the design of your experiment and the way you hold factors constant. And even if you try to hold factors constant in a regression, sometimes doing that math can lead to a worse model than if you controlled for those factors at the very beginning and you made sure they had a very strict and very clean experiment. So what's more important than running these statistics is making sure that your experiment is clean and efficient and elegant. So that's the basic takeaway message from that optional reading, I think it's a good one. And again, with clean, efficient, and optimal, the takeaway message for this data is the bivariate model is the best one we need to look at, and it should possibly use nonlinear transformation in order to get the best results.